it's time to get started, we'll do the respiratory mechanics lecture. This is the anatomy that teaches what we call the mechanics of breathing. What I said last lecture was that the lung wall stuck to the chest wall. However, what I didn't say is that the interactions of lung and chest wall, they are stuck to each other, but not by direct attachment. The through the pleural cavity, which is a fluid-filled space between the parietal and visceral pleura. So let's write that down. The lung wall is stuck to the chest wall through the pleural membranes. It's not a direct attachment. The pleura, the pleural membranes, are like the pericardium. It's a double membrane that covers the organ. So I have a lot of pictures here. So if you look at the picture on the bottom, we call it the lollipop lung analogy. If the lollipop is your lung, and you stick it in a small fluid-filled balloon, which and then completely envelops it, that's pretty much what the pleura is. And the lung is stuck to the chest through that. So if you look at the top picture, the little insect, they take a little bit of lung wall, chest wall there. And you can see there's a gap between the lung and the chest. Now, when I say chest, it's ribs and intercostal muscle, right? But you can see that that little gap is the pleural cavity. The parietal pleura is the pleural membrane that is stuck to what's on the inside of the chest wall. And the visceral pleura is on the outside of the lung wall. So that's what we're talking about. So before I write anything else, I'll say that the pleural membranes are serous membranes. That's why the pleural cavity is fluid filled. So the parietal pleura it's a membrane that lines the entire inside of the chest wall. Your ribs, your muscles, your rib cage, basically. Then you have that gap, the fluid-filled space, the pleural cavity. That's why I said it's a serous membrane. It secretes a fluid, fills that space. That fluid is very important. That is actually what is keeping the lung wall stuck to the chest wall. It's like if you took a little drop of water on a glass plate, and then take another glass plate and put it on top of it. The cohesive forces of that water will keep the glass plate stuck together. You might be able to slide them back and forth, but it'll be very difficult to separate the glass plates. That's the analogy I usually give for this pleural cavity. It's keeping the lung wall stuck to the chest wall because the visceral pleura is on the outside of the lung wall. I'll just say lines outside of lung wall. Now, because the lung is stuck to the chest, it turns out they kind of pull in opposite directions. It's like, let me read my second bullet point. The lungs and thoracic wall, they pull away from each other on opposite sides of the pleural cavity. The intrapleural pressure is less than atmospheric pressure. Well, what I'm trying to say here is the pressure is negative relative to the air you breathe. Let me write that down. The lung wall pulls chest in. At the same time, chest wall kind of like holds the lung wall out. Kind of paraphrasing that second point. Just think of like the lung is like a balloon. If you blow up a balloon, you inflate it, but then if you just kind of don't tie it and just kind of let the bladder go at the end, the air will intrinsically be pushed out because the rubber wall of the balloon wants to elastically collapse. The lung is like that. I showed you the elastic fibers that surround the alveolar spaces. The lung is like a balloon. It wants to collapse, but it doesn't because the chest holds it out. Turn this down a little bit. I mean, look at that skeleton back there. Well, look at it. I got to change my battery. This thing's going out. You have to change it. Wrong size. We're busy. One wall. All right, this isn't working, so no microphone today. So I have to ask you to be quiet. doesn't work. All right, so the lung wall wants to collapse because it's stuck to the chest wall. It pulls the chest in, and chest wall holds the lung out. So because of that fact, when you measure the pressure inside the pleural cavity, it's a negative pressure. Pressure of atmospheric air at sea level, like here in Sacramento or about sea level, it's like 760. Millimeters of mercury, that's about 1 atmosphere. Okay, well we just kind of go with millimeters of mercury. So if we kind of use that as our baseline, you could say, let's just call that 0. That's our 0 baseline. If you were to measure the pressure inside the pleural cavity, because it's like these things are pulling on each other, it creates a negative pressure on the inside. It will be about -4. Or about 756. Okay, so that's kind of what I wanted to say about the pleural cavity. It is a negative pressure. That seal must not be broken. And if it ever is, due to injury, trauma, whatever, that's called what we call that a collapsed lung. You break the seal. In this example, it's a bullet wound. Air rushes in. It fills that negative pressure, and let me write this down. The fancy word for collapsed lung is secondary atelectasis, a collapse of a previously inflated lung. Of course, previously inflated. When did you first inflate your lungs? When you're born. So you can't just say that. But if it does collapse, that's a good picture of it, I think. So what happens is, in terms of pressure, is you have a wound. Let's say air enters pleural cavity. That negative pressure will equalize and become 0. So that means there's nothing, the seal has been broken. There's nothing keeping the lung wall stuck to the chest wall. The lung collapses. Okay, and look at the picture. Did one or both lungs collapse? Just one, because the pleural cavities house one lung or the other. Okay, so that's a good thing. At least you have the other lung working. However, I mean, you can treat this. You can insert a chest tube. You can evacuate the air. If there's fluid in there, well, if air rushes in, they call that a pneumothorax. If fluid or blood rushes in there, for example, they call that a hemothorax. Depending on what rushes in there, this will happen. And you can do needle decompression or insert a chest tube to let the air out or evacuate the fluids. And if you do that, that should help reinflate the lung. But a collapsed lung is difficult to inflate. You basically can't do it on your own. So that's why that pleural cavity is important. So assume there's no trauma. Well, you know, this can happen not just with physical trauma, knife wound or bullet wound. I remember one year I had a student, she, one semester she had a really bad cough, and I remember the next semester she kind of overheard her saying, oh well, man, yeah, I had a spontaneous collapsed lung, and This can happen spontaneously. It doesn't have to happen with a wound. Just by severe coughing, it can happen spontaneously. Hold on a second. I was expecting a different slide. Okay, we'll just go with this. The next topic are the muscles of breathing. There's muscles that help you breathe in and muscles that help you breathe out. The muscles of inspiration, it includes the diaphragm and the external intercostals. Those are the two main ones. Well, this slide only shows diaphragm, so let's start with that. I think this picture is a really good representation of how far up the rib cage it actually goes. It's a big dome-shaped muscle. This picture shows you its action as it is relaxed and contracted. So, when the muscle contracts, it flattens. Therefore, which color is state of contraction? Blue or red? The red shows it a little more flattened. Okay, so that's what you want to keep in mind. So, to make sense of that, look at this picture here. Note the central tendon. It's surrounded by muscle fibers. I shouldn't have to write that. That's why it's called the central tendon. What else would it be surrounded by? So when all the muscle fibers contract, they're pulling that tendon down. Okay, so that's kind of the visual you want to give yourself. Muscle contracts. The innervation is the phrenic nerve. That's the roots C3, 4, and 5. Spinal nerve roots, there's an old phrase in anatomy, C3, 4, 5. Keep your diaphragm alive because of the phrenic nerve. Those are the nerve roots. So know that nerve. Flattens. When it flattens, you're helping to increase the thoracic volume. Decrease intrapulmonary pressure. Running out of room here, but that leads to air flows in the lungs. So that's the basic idea of taking a breath in. There are other muscles that contract too. To finish off the anatomy of the diaphragm, you should know that the function of this is for breathing. But in terms of other anatomy things, it's the border between thoracic and abdominal cavities. It's a membrane. Well, it's a muscle, but diaphragm means membrane. It's a membrane that separates thoracic and abdominal cavities. And you should know those three things that enter through it. There's a cable opening. It's at the highest level. It's at about the level of the T8 vertebra. And through there goes the inferior vena cava. Well, yeah, and as soon as it goes through there, it goes right into the heart. so let me point to it. Cable opening, it's not labeled, but I know what it is. It's the one that's highest up. You see that blue tube going through it? It's around T8. So there it is right there. Okay. Now this hole right next to it is the opening for the esophagus. That's at about the level of T10. Esophageal opening. Esophagus is the food way you swallow food. It goes right down to your stomach, and we'll talk about that later in digestion. And then at T12 is the opening for the aorta, called the aortic hiatus. So once the aorta goes through there, it becomes the abdominal aorta, right? Thoracic becomes abdominal. I'll write that. So thoracic aorta goes through there, becomes abdominal aorta. I won't test you on the attachments. Just know how big it is. It's attaching all the way around the rib cage. And you can stick your head up there. It's really big. It's a big space. I've seen it on cadavers. I didn't try to stick my head up there, but I was impressed by how big a dome it is. I want to talk about the other muscles of breathing. The external intercostals, well, they occupy all the spaces. Notice how they kind of end at the border between where rib becomes cartilage, bone becomes cartilage, right around there. And it goes all the way to the back. Well, anyway, just be able to identify the external intercostal. Not to be confused with internal intercostal. There's also innermost, but you just do external and internal. The ribs are like bucket handles. Each individual rib is curved like a bucket handle, and it's been described that when this muscle contracts, it like lifts each rib below it up, like lifting up a bucket handle. And in doing that, you expand the rib cage laterally from side to side. So I'll just say, in terms of action, elevates ribs. Expands rib cage laterally, side to side. And they actually call the lifting of the ribs this bucket handle movement. Now that's a term that I see in anatomy books. It's on the next slide, but before I get there, on this slide, the one muscle of inspiration I want you to know is the the one muscle of expiration is internal intercostal. Muscle of expiration. So they actually, that layer is internal, but it goes all the way to the sternum. Okay. But anyways, you can identify it there. It's easy to tell on a cadaver which one's more external. They did a pretty good job. You can tell this one's deep. And, well, it does the opposite. It depresses ribs, right, to help push air out of your lungs. Now, normally, you don't have to recruit these muscles to take a breath out. Usually when you're huffing and puffing, like during exercise, strenuous exercise, then you would have to actually recruit these. Because normally you don't have to. normal quiet breathing like you're doing now, you don't recruit muscles. It's just passive. Okay? So depressed ribs during, we'll say, forceful expiration. You'll be doing this in Wednesday's lab. It's a spirometry lab, and normally you don't make effort to take a breath out. But to measure a lung capacity, we have to have subjects take a maximal breath in and then a maximal breath out. That's forcefully, so you can push out all the air as quick as you can to assess airflow. And so you'll be doing that in lab. There's other muscles here that attach to the ribs, and any muscle that attaches to a rib can be considered an accessory muscle of breathing. So I'll just list a few off the top of my head. Well, some that are shown here, the scalenes, these deep neck muscles that attach to rib 1 and 2. So if it attaches on it, you could add it to the list. Scalenes, I'll say SCM, sternocleidomastoid, serratus anterior. It's another one. The pecs, major and minor, pec muscles. Okay, I just gonna list a few there. You get the idea. The concept is any muscle that attaches to ribs can help you breathe. But the three, diaphragm, external intercostal, internal intercostals, I would consider those the main ones. One other thing besides that, bucket handle movement, which I mentioned for external intercostal. Imagine the one set of ribs. I'm not sure which one that is, but if you lift it up, that's like breathing in, because you expand the rib cage just a little bit, side to side. But the sternum has there's a sternal angle there between the manubrium and the body, and that's like a pump handle. And so if you kind of like take a breath in, you kind of like push it out just a little bit, like cranking up a pump handle. And so that expands the rib cage from front to back, from anterior to posterior. So I should mention that too. The pump handle movement, that's at the sternal angle. You're supposed to know that's between it's in your sternum, so it's the sternal angle. It's the joint there that allows the chest to expand from anterior to posterior. Students to know how the chest expands when you take a breath in, from side to side and front to back. All right, so great. You can physically expand your chest, your rib cage. Your rib cage is stiff, right? It's not like a balloon. It's stiff. It's got to hold the lungs out. Okay. I've seen paramedic students administer chest compressions on cadavers so they can practice, and usually you can hear the ribs crack. If you do it properly, the ribs should crack because it's stiff, okay? And you're trying to save someone's life, broken ribs will heal, but the point is, rib cage stiff, good at holding the lung wall out so they don't collapse, okay? You try to compress the ribs, they break. They're not supposed to collapse. So if you can expand your chest, we'll just review gas laws quickly. Now, gas is not like liquid, right? No matter how much gas you have filled in the sealed chamber, the gas molecules will bounce around and exert a pressure to fill the space that you provide for them. So if you have the pressure, if you have the volume, you double the pressure. That's what I'm trying to say. So that's this gas law here, Charles' law. To make sure that this equation stays equal, again, if you change the volume, the pressure increases so that things remain equal. So that's important to keep in mind. And so in terms of us, in talking about humans breathing, we want to change the volume, so we change the pressure inside of our lungs to make air go in and out. Okay, that's what I want you to keep in mind. So the physics of lungs, airways, chest wall, and how they cause changes in lung volume, which create pressure gradients to move air in and out. That's what we're going to talk about for the next 23 minutes. And so it's all about understanding the pressure inside here versus the pressure outside there. Okay, because the goal is to create a pressure difference in here so that air can flow in or out. Okay, it's all about just changing the pressure in here just a little bit, plus or minus 1, relative to atmospheric pressure, to cause a gradient for air to flow. So let's define these pressures. PATM is my abbreviation for atmospheric pressure. I already defined it as 0 or 760. You know, roughly that's what it is at sea level. Okay, we'll stick with that for this lecture. Okay, so I said inside the pleural cavity, let's call that the PIP. Or intrapleural pressure. Let's remember that's the pressure of the pleural cavity. Okay, we noted it before. Here's a question that always tricks students on exams. True or false? The pleural cavities contain the lungs. False. They don't contain the lungs. What's inside there? Fluid. Okay, I already said that, right? They contain fluid. They surround the lungs, but it's the cavity between the parietal and visceral pleura. They contain fluid. The thoracic cavity contains the lungs. That's kind of the, I guess it's not a trick question if I actually told you fluid's in there, but it seems to trick you. Okay, so don't let me trick you. What's in the pleural cavity? Fluid. Fluid, not lungs. So you just go with that. And what number did I give you prior, like -4? Well, that's really kind of an average. The pleural, this pressure changes with breathing, but it always stays negative. Always negative. So let's go with -4. It does change. It gets more negative, less negative, but it stays negative. That's the point with that. Okay. Well, anyways, that other pressure, the intrapleural pressure, that people okay, this pressure is the one that's important. This pressure is always changing. And, well, 0 plus 1, -1. Let's say you change it to -1. That's breathing in. Because if you create a negative pressure inside the lung, inside the alveolar spaces, sometimes this is called intraalveolar. If you ever see that term. Well, anyways, I'll get back to what I was saying here. You create a gradient so air will rush in, until you equilibrate with the atmosphere. Okay, that's taking a breath in. Once you stop breathing in, you can assume that you've equilibrated with the atmosphere during normal quiet breathing. So like when you take a breath out, you create a positive pressure relative to atmospheric pressure, so the air will leave until you equilibrate. So every time you take a breath in, for half of a breath, you equilibrate. Then take a breath out for the other half of the breath. You're always equilibrating with atmospheric pressure. That's the point there. And so what you got to do is just, it's not much of a calculation, but to put it in an equation, you always have to calculate the difference between the inside and the outside. So write this equation down there. Transmural pressure is always the pressure difference between 2 points. We talked about it in the baroreceptor reflex. It's the pressure across the vessel wall. And that was the pressure across the respiratory system. And we're not talking about blood flow, we're talking about airflow. So here I abbreviate transmural pressure PTR. It's always pressure in minus pressure out. By convention, but what's the context? The respiratory system. So what's the pressure in? Well, it's inside our lungs. That's intrapulmonary pressure. Pressure out is the air you breathe, so the atmospheric pressure. So that's basically what you have to compare to see if air is flowing. So again, just to show you that picture again, so it's just the difference between pressure in minus pressure of the air you are breathing. So what you can do is, well, we'll have to now teach the forces acting on the lung wall and the chest wall, because you have to consider that too. And what I said earlier this morning is the lung holds the chest in, the chest pulls the lung wall out. So what are the forces acting on the lung and on the chest wall? And so I kind of put some pictures to visualize what we're talking about here. Well, let's call this the intrinsic forces of lung and chest wall. I said the lung is like a balloon, like the rubbery balloon wall. If a balloon is inflated, if you want to let the air out, the balloon will collapse. Okay? And the lungs are kind of like that because of all the elastic fibers that surround the alveolar spaces. So number one, I'll call it elastic recoil. It's an inward force. It wants to make the lung collapse like a balloon. Of course, it won't ever completely collapse unless you break the seal, right, of the pleura. But it's a force. I always just say it's a force in. It makes the lungs go in. And well, I should mention that. Remember when I draw the alveolar space like that, and you can imagine there's like little water molecules that line the surface. So there's like this water-air interface inside your little alveolar spaces. I said in the anatomy lecture you have like 600 million of these spaces. The thing about water is the cohesive forces are so strong, like each little water molecule is attracted to each other. And because they're arranged in a circle, it creates this inward force that wants to make the lung collapse. So we call these the surface tension forces. So often I'll just kind of abbreviate these two things. ELST, if you ever see that. But both are forces in, right? They both want to make the lung collapse. And this point illustrates why you need the type 2 cells to secrete surfactants. Surfactants are like detergents. They insert themselves in between water molecules. So imagine like surfactant. So when you break those cohesive forces, you decrease that inward force. It makes the lungs easier to inflate. You're decreasing the viscosity of water, and that's why detergents can get your clothes cleaner. If you decrease the viscosity of water, the water molecules more easily penetrate the fabric of your clothes to get the stains out. Well, anyway, same principle inside the lungs there. But both of these are the intrinsic forces for the lungs we want you to consider. So I guess I should title this lungs. For chest wall, I left myself a smaller space there. I said, yeah, look at the rib cage. I said, when you can try to compress ribs, they break. It's like a stiff cone cage, right? If this is like a balloon, this is like a force in the opposite direction. So the elastic recoil of the chest wall doesn't want to collapse. It wants to expand the lung. So I say that this elastic recoil force is out, not in. Number 1, coil. So the lung has elastic recoil and surface tension, but there's just kind of like elastic recoil for the chest wall. They're just kind of like, I've heard this analogy given. It's like the springs are pulling in opposite directions, and the lung and chest wall are stuck by that little slim layer of fluid in the pleural cavity. The lung holds chest wall in and chest wall holds lung out. When you breathe in, those forces at the chest wall are greater. So they pull the lung wall out with it, and that helps draw air into the lungs. But then when you relax your muscles of inspiration, it's the opposite way. So it just kind of goes back and forth like that with each breath in, each breath out. So think of it that way, that the spring is pulling one way or the other. So it's important for students to understand this interaction of the transmural pressures and these intrinsic forces. Okay? They kind of go together. Let me write this down. So what we're going to do now is we're going to apply the relationship of transmural pressure and intrinsic forces breathe on lung and chest wall. During a breath. And we're going to divide a breath into 3 parts. Something I call FRC, then inspiration, expiration. Now, this I haven't taught yet. FRC is a lung, it stands for functional residual capacity. Okay, I don't know if you need to write that down now, but I'm going to define it later. Let's just say this is the moment before you take a breath. Okay. Breathe in, breathe out, pause. That pause is before you take your next breath. Think of it that way. Moment before you inspire for the next breath. Okay, I want to consider that moment. Then breathe in, breathe out. Inspiration. For the expiration. So we have to consider, I'll underline it, this and this, okay, during each breath. And sometimes students don't know where I'm going with this. Let me see if I can clarify giving this balloon analogy that I list here. I remember this was kind of given to me as a student to kind of help me understand, because the idea of a balloon is easy to understand, because I think everyone's blown up a balloon. When you blow air into the balloon, there's air in there, and it's pushing against the balloon wall in all directions, right? Let's just say there's plus 10 air in there. Okay, so the thing about the transmural pressure P in minus P out, we can assume that the pressure outside the balloon is atmospheric pressure, 0. If you were to apply this equation to these numbers, it's easy to do, but I have to set conventions. For transmural pressure, if you do your math and you get a positive number, that's a force out. Okay, that means out. So negative is in. All right, so let's kind of do the math here. What's the pressure inside the balloon that I set? Plus 10. What's the pressure outside the balloon? 0. So 10 minus 0 is 10. So is that a force in or a force out? It's positive, so isn't it? Out. It's a force out. And I remember my professor asked me this question. Oh, well, is the balloon expanding? I was like, what? Well, if I had a balloon here and I tied it off, is it expanding? You guys know what a balloon is? And once you tie it off, is it expanding? Yes or no? No. I was like, what is he talking about? No, it's not expanding. So I know what a balloon is. What? This is a good question, because we just said there's a force out. How come the balloon isn't expanding? What's resisting that outward force? The balloon wall, right? And like, this is something you don't think about when you blow up a balloon, but that's what I'm talking about here. What's the intrinsic force on the balloon? What's the balloon wall made out of? Rubber or elastic? I don't know. But the point is, he was like, okay, so calculate the force of this intrinsic balloon wall. Well, what is it? If the balloon's not expanding, shouldn't it be equal and opposite? Wouldn't you say -10? Well, yeah, you would. Well, anyways, that's what he went through that exercise. He was trying to show us that you can't just calculate the transmural pressure. You have to consider the material, okay? That's why I went through this whole thing of defining. This, like, what are the intrinsic forces? You're going to inflate it and then not, and what is this? And you have to kind of consider all that. So, I mean, I think that's kind of where we try to get students to think about in respiratory mechanics. And it's something as simple as a balloon, like you even have to like do deep thinking just for a balloon. So think how much more complicated your actual lungs are. And you know, we really make it as simple as possible, but once you go through it, like breathe in, breathe out, it's really not that difficult to understand. Anyone going into the respiratory therapist program? So this is kind of, I think we all should understand this, but these are the kind of things where if you're having trouble with this lecture, maybe you should consider a different field. There's a lot of fields to consider. Yeah, question?
Is this the type of equation you would use to determine if a patient's got like COPD or something like that?
There's too many variables there.
Oh, okay.
This is like way, way simple, but it's one of them.
Okay.
For like COPD, it'll be like, you have to generate so much more of a difference to draw air into the lungs, depending on what's causing the COPD. Yeah. But in healthy lungs, you just have to create a little bit of a difference and air will move in and out quite easily. All right, so let's start with, let's start with before you take a breath. Let's start with FRC. And here I say nothing's moving because you haven't taken a breath yet. Okay, it's that moment before you take a breath. So I have lung and chest wall forces. I'll just do CW chest wall just to be brief. Now look how I drew the arrows. I'm saying nothing is moving, and well, even if you haven't had physics, if nothing is moving and things are pulling in the opposite direction, you can conceptually understand that these forces are equal. They're pulling in the opposite direction, but you're not moving this way or this way, so the forces are equal. Okay, before you take your breath, your chest isn't expanding or collapsing. This is the moment before you take your breath. So that's important to note, that the forces are equal. That's why nothing is moving. So, let's do our PTR equation. I gave you three numbers for that p-pole. I gave you 0, +1, -1. This is before you take a breath. What do you think it is? It's 0. You haven't done anything yet. What's pressure of the atmosphere? That I've been saying all morning? 0. And this math isn't hard. I don't think you need a calculator for that, do you? What's 0 minus 0? 0. So the math is easy, but what's the concept? What does 0 mean in this lecture? It means there's no gradient for air to flow. Air is not flowing in or out. There's no airflow, right, before you take a breath. So the forces are equal. Your chest wall, lung wall, nothing's moving, and everything's equilibrated, no airflow. But that's not breathing, right? We need air to flow, so let's take a breath in. Inspiration is an active process, so write that down. Keyword active. So what that means is you recruit muscles. The nerves fire. Muscle, phrenic nerve. And, I didn't give you the nerves to know for the external intercostals or the scaling muscles. Don't worry about it. But do know the phrenic nerve. Okay, that's not basic anatomy. So anyways, recruit muscles. And let's go with diaphragm and external intercostals. Don't worry about the scalings. I don't know why I have those there. Let's go with diaphragm. External intercostals. So I'll just list them. I already talked about how they expand the rib cage. The general idea I want you to get is when you recruit these muscles, you increase thoracic volume. So, the chest wall forces are greater because these muscles are making that so. Put greater so it's clear. That's the greater than sign. These forces are greater than that. So when you increase the thoracic volume, your rib cage expands, and what that does is it decreases intrapulmonary pressure. People. All right, so for our pressure over here, so our intrinsic forces, you made your muscles contract and they're expanding the chest wall. You've increased thoracic volume and you decreased the intrapulmonary pressure to maybe just like -1. And it's always millimeters of mercury, although sometimes I don't use it, just to be brief, but it's always millimeters of mercury. So in calculating the atmospheric pressure, the transmural pressure across the system is -1 minus 0 is -1. Okay, again, the math isn't hard, but the concept is, well, that's the pressure in. So now there's a vacuum. We breathe by negative pressure. We inspire air by negative pressure. Okay, and this might go against the convention. We don't inflate our lungs. We create a negative pressure and air rushes in. Okay? So air rushes in until what? Until you equilibrate to 0. Then air stops flowing at the end of a breath in. That's it. So imagine this is a model of the lungs inflating with air. You first recruit the muscles, you expand the lung wall and decrease the intrapulmonary pressure to -1. Then air rushes in to fill the vacuum until 0. Right? So let me do it one more time. So see, lungs are small, lungs are bigger. You decrease the pressure, then air rushes in. So think of it in that way, even though really it happens simultaneously. Okay, but I want you to first know you create the negative pressure to cause the air to rush in. That's why we talk about the transmural pressure. Because your lungs are in communication with the outside world through right here, correct? Through your airways. So that's why we taught the airways first. So any questions on taking a breath in, inspiration? So I'm gonna move to expiration. normal quiet breathing, expiration, a breath out is a passive process. Well, no muscle recruitment, okay? You just kind of let the muscles relax and the lungs recoil. Muscles of inspiration relax. Lungs recoil. So these forces become greater. And the lung, like a balloon, it just, I mean, they don't collapse all the way, right? I mean, it's not a collapsed lung, but enough to allow the chest wall to decrease. You decrease thoracic volume. Therefore, the gas molecules now have less room to bounce around, so you increase the intrapulmonary pressure. P-pole. Okay, so to go to our equation here, you increase it to say +1. -0, so it's a positive number. Positive like a force out, so basically the air rushes out until you equilibrate. Until you reach 0. Okay, so that's a breath in and a breath out. So this kind of pick up where we left off. We took a breath in, we equilibrated, now a breath out, things collapse. That creates a positive pressure inside the lungs. And then air rushes out until you equilibrate. So I'll do it one more time. Okay, so basically, end of a breath in, we're at 0. Things collapse. Positive pressure, air rushes out until you equilibrate to 0. So we have this in graph form too. Here's the graph I would study. Look at the top graph. Well, I have the bottom graph too. The middle graph I really don't teach. The middle graph, well, I taught, but it's intrapulmonary pressure. And what's the number I gave you to know for the PIP? The negative pressure that keeps lungs stuck to chest. -4. So I just gave you an average of this. It changes with breathing. Don't try to understand why or how. I never even gave that much thought. But it's always negative relative to atmospheric pressure. Okay, that's the thing to keep in mind for the PIP. So this is the whole, well, let me go through it. I said inspiration, expiration. They say inhalation, exhalation, same thing. Intrapulmonary pressure, they just kind of point to a space inside the lung. That's okay. Right, so what I did was I kind of did my little own illustration, and I said, look at the green dot. We started at FRC, right, where it's all zeroed out. But then when you take a breath in, you expand the chest wall, and the lungs expand with it, creating a negative pressure inside the intrapulmonary space, -1. Then what? Air rushes in until what? You equilibrate to 0, so that's where we are. Then I said when you take a breath out, you create a positive pressure, then air rushes out until you equilibrate with 0. So that's the whole point of breathing. With each breath in and breath out, all you're doing is equilibrating with the air you're breathing. That's it. Okay. Now, other topics to address include things like lung compliance. A compliant lung is good, basically. It means it's easier to inflate. If you have the surfactants working, you're decreasing those surface tension forces that I talked about, okay? So normally, with surfactants, we only need to generate 1 to 2 millimeters of mercury to get air to flow. But without surfactants, well, the lungs are much more difficult to inflate, so you need to generate, but this is difficult breathing, basically. If you have to generate more pressure to get air to flow, it's not good. That's a lung that's stiff and not compliant. So I want to give one slide why surface tension forces are important for lung compliance. So as a review, over here when I gave you these notes, for number one, at FRC, what dominated? Or were they equal? Equal. But what about when you took a breath in? What dominated, chest or lung? Chest, and then you take a breath out, those muscles relax, and then the lung wall forces are greater. So let me show you the classic bell jar model of lungs. It's over here. I have to go into the cabinet. So in this model, what do the balloons symbolize? Lungs. Excellent. And we have our airway here. This stopper's got a hole in it so we can allow air to ventilate. And the actual bell jar will represent, I guess, thoracic cavity. But what does this rubber membrane represent, you think? Diaphragm. And so by changing the diaphragm, you can change the volume in here. Let me make sure this is a tight seal. Okay, so if I pull down, what should happen to the balloons inside? Should they inflate or not? If you increase the thoracic volume, what happens to the pressure inside the balloons? It decreases, so air should be sucked in. So if I pull down, they inflate a little bit. If I push up, they deflate. So if you pull down, they inflate, and this simulates breathing, right? That's why it's a good model. All you do is pull down and air goes in. Okay, I'm not blowing air in there, am I? No. You just pull down and they inflate. So that's why it's a good model to kind of illustrate this concept. Okay, if you increase the pressure, inflate. If you push up, air goes out. And of course, if you break the seal, well, it still works pretty good. But if you completely break it, then obviously it's not going to do anything. What is that like? The pneumothorax? Again, a knife fight?
Knife fight.
Well, hopefully, I'm just joking. People actually do get in knife fights, but. Okay, so that's kind of what I had there. This is a good spot for a break. We'll talk about other topics when we come back.